In this math talk, we keep adding to our exponent rules, and we're going to extend them into the negative exponents now. And we begin with the question, evaluate 3 to the negative 4. And one note we need to make right now is that negative exponents are really more of a definition, kind of like the zero exponents, to keep our exponent laws consistent. So we're going to begin, in this case, by looking at 3 to the exponent 2 divided by 3 to the exponent 6. And I'm going to use our division of powers to examine this question. So here we go. I write 3 to the exponent 2 divided by 3 to the exponent 6, and I apply the rule that says when dividing two powers with the same base, keep the base the same, subtract the exponents. So it goes like this. Leaving the base the same as a 3, subtracting the exponents, I'd say 2 subtract 6. That would give me 3 to the exponent negative 4. Now, we're going to look at it a second time this way by expanding it. So we'll look at 3 to the exponent 2 divided by 3 to the exponent 6, and we'll write it in expanded form. 3 to the exponent 2 means 3 times 3, and 3 to the exponent 6 means 3 times 3 times 3, and so on, and so on, and so on. So 6 of them. Now when we look at reducing that fraction, here's what happens. Those two 3's can reduce to produce 1's. Those two 3's can reduce to produce 1's. And we are left simply with a numerator that is 1 times 1, which is 1, and a denominator that's 1 times 1, and then 4 3's multiplied together. Well, the 4 3's amount to 3 to the exponent positive 4. And that looks pretty interesting. I mean, we started with the question of 3 to the exponent negative 4. So 3 to the exponent negative 4. And it turns out to be 1 over 3 to the exponent positive 4. And that's worth just summarizing here. 3 to the exponent negative 4 is 1 over 3 to the exponent positive 4. Well, it sort of looks like in order to deal with a negative exponent, you just flip that power upside down and switch the exponent sign from a negative to a positive. Well, that's exactly what you do. And the law is stated this way. It looks like this. A raised to the exponent negative n is simply 1 divided by a raised to the exponent positive n. You notice I do nothing to the base. All I do is flip this and turn it into a fraction and give the base a positive exponent instead of a negative. Our one condition on this is that a itself is not 0, because that would lead to division by 0 once we flipped. There are two other variations on that are worth writing down. If we have 1 over a to the negative n, like that, so the power with the negative exponent is residing in the denominator, well, it looks like this. A to the exponent positive n. And then finally, one that's really useful is this one. When I have a divided by b, so I've got a fractional expression, a fractional quantity in brackets raised to a negative n, I simply flip that and make it b divided by a to the positive n. Now I want to make one more point with you. I want to show you why this is consistent with our rules. Let's consider 3 to the exponent 2. We understand that to be 9. 3 to the exponent 1 we know is 3. 3 to the exponent 0, when we looked at 0 exponents, we discovered was 1. What we discover is that as I continue to drop that exponent by 1, so here I'm dropping that by 1, and I drop it by 1 again, we notice that we divide by 3. So 9 divided by 3 would give me 3. 3 divided by 3 would give me 1. Well, if I were to drop it one more time, so if I said 3 to the exponent negative 1, I would divide this answer here by 3. So that gets divided by 3 one more time. Well, 1 divided by 3 is just 1 over 3. So that'd be 1 over 3 to the positive 1. In fact, we could go one more on that. If we drop that exponent one more time, so from 0 to the negative 1 and then from negative 1 to negative 2, it becomes 3 to the exponent negative 2. When I divide this fraction, when I take a third and divide it by 3, 1/3 divided by 3 is 1 over 9, or the equivalent of, just as a side note, 1 over 3 squared. So that all seems consistent. Now let's apply it in some examples. Okay, quite a few examples to go through here. I've got the 3 rules written at the top that we're going to make use of. A to the negative n equals 1 over a to the n. 1 over a to the negative n is equal to a to the n, and a over b to the negative n is b over a to the positive n. In all of this, a can't be 0, and certainly in the fraction situation, a divided by b, we understand that b itself can't be 0. Okay, here we go. Let's evaluate. Starting with 7 to the negative 3, the first thing that I will write is that that is 1 over 7 to the positive 3. Notice I did nothing to the base. I didn't make the base negative. I didn't change it in any way. I just made it 1 over 7 to the positive 3. 7 times 7 times 7 is 343. There we go. So we've evaluated that. The second one, negative 5 raised to the exponent negative 4. Well, that's going to be 1 over that same negative 5, unchanged, to the positive 4. 4 negative 5s multiplied together are 625. So our answer is 1 over 625. Moving on to 5 over 6 raised to the negative 2. That is our fraction rule, where we're going to just take it and make it 6 over 5 to the positive 2. At that point, we apply the power of a quotient rule, so that gives that exponent of 2 to the 6 as well as the 5, and we're left with 36 over 25. Now we're getting away from evaluation. We can really only simplify these next examples because we've got some variables in them. Well, the rule still applies. My base is 2x, my exponent is negative 5. I write that as 1 over 2x to the positive 5. Well, extending that, I say 1 over 2 to the 5 x to the 5, which is your power of a product rule. And that finally becomes, I'll squeeze it in right over here, 1 over 32 x to the 5. Now, this next question looks a lot like the last question, but we remind ourselves that exponents operate just on the thing to their left. So this negative 5 belongs to the base of x, but has nothing to do with this 2. So in order to answer this question, we write 2 times 1 over x to the positive 5. So that's 2 times 1 over x to the positive 5. Well, we treat the 2 as 2 over 1, and so we get an answer of 2 times 1, which is 2, over 1 times x to the 5, which is x to the 5. Just 3 more to go. Using that last concept and recognizing that exponents operate just on what's next to them, we have the negative 3 operating on just the m here, and the negative 1 operating just on the n here. Watch what happens. Kind of like the last example, the 2 stayed where it was, and the x to the negative 5 ended up in the denominator. This works very much the same way. The 2 and the 5 don't have any exponents on them. They stay where they are. But the m to the negative 3, because it's got a negative exponent, will come downstairs. And the n to the negative 1 with the negative exponent comes upstairs. And that's your final answer. A couple more evaluations here. 2 to the negative 2 is 1 over 2 squared, plus 3 to the 0 is 1, plus 4 to the negative 1 is 1 over 4 to the positive 1, or 1/4. Well, that's 1/4 plus 1 plus 1/4. And that's, well, let me see here. That's 1.5, or 3 over 2. Moving on, just one last one to go. Applying BEDMAS, we're going to work the two sets of brackets separately. 2 to the negative 2 is 1 over 2 squared. Plus 3 to the 0 is 1. Divided by 4 to the negative 1 is 1 over 4. Minus 5 to the 0 is 1. That's 1/4 plus 1 divided by 1/4 minus 1. That becomes 5 over 4 divided by, that will work out to negative 3 over 4. Just to finish up, when we divide two fractions, we invert the second fraction and turn it into a multiplication. So this becomes negative 4 over 3. I'm going to reduce the 4's because we always do that when we're working with fractions before we multiply. And I end up with a final answer of negative 5 over 3. Wow, that was a lot of examples, but it sort of covers a pretty important topic. And so now I'm out of time.